there are no work and energy questions on the exam, just like there's no force questions on the exam. They don't tell you what the problem is before you start it. Most of the time, it's going to be more than one thing that you're going to have to do. So there are clues as to which way you should go to solve a problem. And when it comes to the AP exam or any kind of problem-solving situation, some of the material we've talked about lends itself better to certain types of problems than it does to others. However, Newton's laws will always lead you to an answer, but that's like the hardest way to do it. So that's why there are other ways to interpret a problem. When it comes down to force or an acceleration, you're probably stuck with Newton's laws. So if they ask for the size of an individual force, or if they want the acceleration of the system, it's probably going to be this. It doesn't mean it has to be. There are other ways to get this information, but you know that this will work. So if they start talking about forces, this is it. And if it's a statics problem, meaning the net force is zero and the object doesn't move, there's only going to be Newton's laws. It is the only way. So for statics, where the system doesn't move, you're stuck here. Anything where the net force is zero, there's just nothing else that's going to solve the problem besides Newton's laws. Now, if they're talking about velocity and displacement, so you have questions about how fast something's going, or you're given information about the change in velocity, and they talk about how far it moved while that happened, that's almost always going to be a work or energy problem. So you're looking at a change in velocity, a change in position, and a change in height. You see any of those kinds of things in the problem? Yes, Newton's laws could solve them, but you'll probably find that the problem will be easier if you use information about work and energy. Now, continue with this, if there's questions about velocity, but they also mix in things like time, energy problems are not suited for problems that deal with time. You'll notice T hasn't shown up anywhere in any of our stuff. So if you start seeing stuff about velocity and time, this is probably momentum, collisions, or on the outside chance, it'll be power. They're going to mix all of this into single problems. You're not going to get escape. You're not going to get to use just one of these. You have to be able to switch from one to the other and know when, there's no choice but to do it this way. But this should help you begin to segment, when can I use this information? When is this the best way to go? Because you see, so far, your tests have been largely, I've told you what's going to be on it, and you've gone in knowing that you're going to have to do a free body diagram and net force equals this or that. But that's not how the AP exam works. And as our skill set grows, you have to understand that all of our tests are cumulative. Your next test is going to have work energy problems on it, where you might also have to do Newton's laws on it. You don't get to just stick with just one thing the whole time, because the AP exams only give you three FRQs, and the entire scope of our class has to be somehow squished into those three FRQs. And so they're going to have everything on them. So what I'd like to do is I'd like to do some example questions, and I'm going to start with kind of the physics honors version of this. So for those of you who are more advanced, understand that I'm starting here because I said I would start every lesson as if you guys have never done this before. But I'm going to be giving you questions that are at your level, while I'm also trying to move the people who have never done this before up to your level. And generally, if you're asked to find a force, Newton's laws can do that. But that doesn't mean it's exclusive. Sometimes you can find a force using any one of these things. We know that force is involved in calculating work. And let the old man just talk. So here we go. This is our first example, and this is a very bare bones basic example. It's just to understand the mechanics of how working with energy and the concept of work is different than what we did with Newton's laws. Newton's laws was very prescriptive, but required a lot of overhead. Doing work energy problems, not so much. But work energy problems are about tracing the energy, accounting for the energy. And when I say that the word accounting, I mean like an accountant. You are accounting for all of the energy in the system. So it's your responsibility to trace where the energy goes in a system. That's how using work and energy helps you solve a problem. So let's consider a problem that's very straightforward. Frictionless surface, and spelled frictionless wrong, and let's go with a simple applied force of 15 newtons at an angle of 30 degrees. Box is going to slide 10 meters across the floor, and it's a 20 kilogram box. If it's a frictionless surface, I think you would all agree that if you push on it for any kind of distance, by the time it makes it across the floor, it's probably moving. Let's assume it started from rest. So I'd like to know, how fast is the box moving after you're done pulling on it? Now, this is like honors physics level question. So this is not the level I need you to work at. We're going to escalate this problem in a couple of steps, but let's start with this basic problem. There's every telltale reason to believe working energy is the way to go here. First, I talk about applying a force, which might make you think Newton's laws, but I clearly give a displacement of the object, and I'm asking for how fast it's going. Those are huge clues that you would go for work and energy and not Newton's laws. But Newton's laws will solve this problem. If you use Newton's laws, you can get an acceleration. And once you get an acceleration, you can put together all of your variables here and begin the process of figuring out how fast it's going after it's been pulled those 10 meters. Newton's laws will solve this problem because it will give you one piece of that puzzle of all 5 motion variables. But it's laborious. You got to put a free body diagram together, figure out what component of the force is in the direction that's being accelerated, deal with the fact that in the y direction the net force is 0. There's a lot there. Work energy is a little different. The definition of work is clear. A force used to cause a displacement. So this is my definition of work. I have 2 definitions. And when I say definitions, equations. It allows me to calculate how much work is done. There's 2 of them. This one is the basic algebra version. And then there's also my more robust calculus version. You have to decide which of these applies to your problem. When you're dealing with work, there's no reason why we couldn't have one or the other. The bottom one, though, that's any time the force is changing over the course of the displacement. So it could be changing the angle, like the person isn't pulling in the same angle the whole time. It could be that they pull hard sometimes and less hard other times. It could be that the ground is uneven and therefore friction is changing all the time. That's when you would use the integral version. That's when you would have to break it up and figure out little sums for moving it a little bit at a time. If the force is constant over the whole interval, though, you can ignore that one and use the top one. So understand we will see the bottom one, maybe even today if we go fast enough. Third period didn't, but we'll see how fourth period does. So let's start with understanding that this force is a constant, and therefore this force is going to do work based on our algebra equation. Now, you'll notice there's nothing in there about how fast it's going. However, you can evaluate a situation and decide whether there is a positive amount of net work. Remember, net work is the sum of all the work that's done on the object. If there's excess work done, meaning this number is not 0, then that energy has to go into changing the velocity. That's what this says. If the net work is 0, then the object velocity is not going to be changed. But if there's more work done, if it's excess, then the object's going to speed up. If there's a deficit of work here, then the object's going to slow down. Ultimately, the only place excess energy goes is to changing the velocity. So we need to look and see what possible things can be doing work on our object. I would argue that there are three forces acting on the object. Would you guys agree? Some of them do work, some of them don't. Let's identify. Let's see if there's more than one that does work. The pulling force, does it do work on the object? Sure does. Yeah, that one's easy. I've got 15 newtons applied for 10 meters, and the angle between the displacement and the size of the force is 30 degrees. It's clear, it's delineated in the problem. And yeah, it's that much plug and chug. This is how much work that force does. And this one's, I don't know, pretty easy, isn't it? Work it out, you get what? Let's make sure you guys can do it. I don't want to be the only one to do it. And you tell me it's 130 joules. 129 point something, but 130 will work. So this is the work done by the applied force. I don't know if that's the net work yet. Because in your notes, be clear. Net work is the sum of all the work done on the object. Don't assume that this is the net work. Make sure you know whether it is or not. They don't have to tell you everything. They can be deceitful. They're asking you to trace the energy. So whoever's pulling on this box is adding 130 joules of energy to the box. Now, weight pulls down. Any reason to believe this downward force is doing work on the box? Is there any component of it in the direction of motion? If there's none of it that points in the direction of motion, it doesn't do work on the box. So there's no work done by gravity. Now there's a normal force upwards, and that normal force isn't equal to the weight because I'm pulling upwards on the box a little bit. Is there any component of the normal force in the direction of motion? It doesn't look like it, right? It's straight up and the box is going to the side. In both of those cases, the angle's 90 degrees. They will not have any contributable work done to the system. They're not adding energy to the system. We were told it's frictionless. So unless there's another force that acts on the object, this is the only work being done on the object. So you should figure out how fast the object is going now. You know the net work. Take a minute and tell me how fast the object is going. Net work is 130 joules. That has to equal the change in kinetic energy. Take a minute, do the plug and chug, find out how fast it's going now. This part's not hard. Change in kinetic energy. So if you need to look in your notes for kinetic energy, that's fine, but I'm hoping that you will memorize it. 1 FMV squared. So, look, my job here really is to call out people I think can't get me the answer. Oh, I have Kleenex. But looks like you're all right. But people have been so kind as to bring in Kleenex, so. I'm gonna stay away though. Sorry. My mask on, you eyes are all snotty. That cold is fierce, isn't it?
Yes.
It's like ripping through you guys. Your immune system's just so sucky right now because of that whole year wearing masks. There was no colds last year. I don't know if you guys recognize that, but nobody got a cold or the flu last year. It was amazing. Of course, I don't know what anybody looked like last year either, so there's that. But you guys, your immune systems are a mess. And the flu, boy, that's ripping through everybody too. Suckers. All right, so let's see. I should just pick out anybody, and I want to be really clear. This shouldn't have been tough. So what do you got?
3.6.
Yep. So velocity is 3.6 meters per second. Square to 13. So again, this, I think, basic kind of level problem. Find out how much energy was given to the box. Use that to figure out how the velocity changed. Easy enough? Now, trying to ease you into this, but this is clearly not the level I want you to work at, right? So let's get to the level I want you to work at. You actually perform this, and you find that when the box makes it over here, it's only moving 2 meters per second. Probably suggests something else is acting on the box. Perhaps it wasn't frictionless. Perhaps it was, friction full, or maybe there was something else. But clearly, something else is going on. Fair enough? All right, so you guys who are advanced a little bit, have had a course in physics, you should figure out what the coefficient of kinetic friction is. You have the skill set to do it. I'm expecting that you can figure that answer out. You guys who are, this is the first time, here's what I want you to find out. I'd like you to find out how much work was done by friction. And if you don't know where to start, I'm going to give you a clue. In this problem, with this modification, I've given you everything you need to figure out the net work first. Because I've told you what the change of kinetic energy is. By giving you the final velocity, I've given you the change in kinetic energy. So you should start by finding out how much net work was done on the box. I'll give you a second to kind of put that together. Net work. You had sufficient time to kind of work that out. You guys who are going ahead of me, keep going. But do we have any difficulty figuring out the net work done on the box? So 40 joules. Now, we know that force did 130 joules. Now, when I say that you have to account for all the energy that is in a system, 130 joules was given to the box, but at the end of our motion, only 40 joules are left in the box. So we've already established that work done by normal force was 0. Work done by gravity was 0. But clearly there must have been work done by some other force. Net work just means adding up all the work. These are scalars. They don't have direction. So I started with 130. I ended with 40. How much work was done by some other force? It's quite literally 90. Now, it's 90 joules, but it has to be negative. This energy was taken away. I gave the box 130. It ended with 40, so there had to be negative 90 joules of work done on the box by something. Not exactly sure what, but I think it's not unreasonable to believe that friction was acting on the box. It fits the bill as a force that would cause negative work. Box is moving to the right. Friction, in this case, acts on the box to the left. It seems very reasonable then that friction is going to be a negative work, because I'll have that cosine of 180 in there, right? In fact, I think we could probably figure out the size of the frictional force. Now, notice I'm bringing this up right now. In these problems, although I am asking us to find a force, we're going to use work to find a force. I know just a minute ago. So we're going to use the information about work to figure out the size of this force. And I hope that you see why. The definition of work is still force times displacement times the cosine of the angle. We know friction acts at an angle of 180 degrees and acted over 10 meters. And we also know it had to do negative 90 joules of work. With that in mind, I don't have to do free body diagram or nothing like that to know that I could probably figure out the size of that frictional force. Cosine 180 gives me my negative 1. Divide both sides by 10, and I find that the frictional force equals 9 newtons. So you can use work to figure out a force, sure, but you're going to need information. You're going to need to know how far you moved. You need to know how much work was done. But you can find that. Now, here's the problem. There's absolutely no way to figure out the coefficient of friction without doing Newton's laws, which is why I told you these problems are cumulative. Work can only get you so far, but eventually you're probably stuck. The net force is 0 in the y direction. Whenever there's a net force of 0, Newton's laws is your only thing to go to. You can't use anything else. And we need the normal force. Whenever you're asked for a coefficient, there's no way to get to that coefficient without knowing the size of the frictional force and the size of the normal force. There's just no way. So work will get you so far, but you're going to have to, sometimes just do the leg work. I'm looking just in the y direction. Normal force is up, weight is down, and there's a component of that force that's upwards too. So I'm going to have to do the hard work here to get the normal force. That's not terribly hard. And you can figure this out. You can get the normal force from this, and once you get that normal force, you can figure out mu. We've done this problem in our last unit, but you're going to have to know when to switch from sticking with work and trying something else. There's no way to get mu directly from work. There just isn't. You're probably going to have to use some form of Newton's laws to be able to get there. But you can see the part where work does kind of fill in, I hope. This example begins to get into the category of mechanics. This last question where you actually have to figure out mu, that's getting in there. Questions about this one? All right. We're going to increase the level of difficulty a little bit, okay? Not much, but I do have something that I really need you to see. I know I'm limited on time, so all right, so I got a 5 kilogram box. And I don't know why I chose 5. My other class I chose 2, but okay. And we'll say the length of this ramp is 10 meters. Angle of the ramp, 30 degrees. I would like to know the minimum amount of work to slide the box from the ground to the top of the ramp. And we'll even make it easy on you and say that the ramp is frictionless. The minimum amount of work done to slide the box up the ramp. Now, you guys who have done problems in physics before, no, you can do this. You should do this. You should not wait for me. You should get towards an answer. You guys who are new to physics, that word minimum should set you on your heels a minute. And you should be thinking about why would they use the word minimum? And let's think about it for just a minute. Work is about a force. So the minimum amount of work still comes down to dealing with these 3 things. D's got to be 10. The only way I get it to the top of the ramp is if I go up the ramp. The angle of the ramp is something I can't choose. The only thing I get to pick is how much force I apply to the box to get it up there. So when we're talking about a minimum amount of work, let's think about the force we would use to get it up to the top of the ramp. If I don't push hard enough, I can't get up the ramp at all, right? It'll just slide right back down on me. But if I push too hard, when I make it to the top of the ramp, it just keeps going off the ramp. The minimum work would be the work necessary to apply a force that is the minimum force necessary to get up the ramp. I'm thinking about we probably need a force where the net force is 0 to go up the ramp. That would probably be the minimum amount of work that would still let the box get to the top of the ramp. So we're talking about what would it take to push the box at constant velocity up the ramp. That's what we're talking about here. Now, I would like everybody to already know exactly how much force that is. I would really like it if everybody knows that. I'm afraid that that's not something that's true for everybody. And that's why I'm a little bit, I need to be cautionary here. This is a ramp. There is nothing special about it. Gravity is pulling down this way with mg sine theta. If I want to push the box up the ramp, I have to push this way with an equal amount of force. That's the minimum. So don't be scared away from the word minimum here. Just understand that minimum is going to generally mean the least amount of force that still allows the box to move or slide or do what it has to do. Working on this question when the bell got us, remember? In the interest of time, although I think we have extra time because of the luncheon thing, so I don't think I have to go too terribly fast here. I got a lot of pushback about this idea of minimum. So I want to come back to this. And instead of talking about pushing the box up to the top of the ramp, I want to do the problem in reverse. I think it might be a little easier for you to see it in reverse. And so to do that, consider instead if the box were already at the top of the ramp. So instead of pushing the box up the ramp, I'd like to know how much work was done on the box as it slides down the ramp. It's a little easier to do, and maybe for a first time, for some of you, this might be a better place to start. And to do this, I want you to consider that you already know what forces are acting on the box. So I don't have to worry about this whole idea of minimum. How many forces are acting on the box? 2. If there's no friction, there will be normal force and weight. And I believe I was a 2 kilogram box, so this is 20 newtons. It's a 5 kilogram box, so 50 newtons. 10. So you guys had a completely different set of circumstances. Now, there is the possibility of 2 different forces doing work on the box. Work done by the normal force and work done by gravity. All right? Consider for a moment that in both cases, the forces are constant, so it's force times distance times the cosine of the angle between them. I don't know what the normal force is. I could probably figure it out. I just don't want to. And here's why. Even though the distance is going to be 10 meters, can't you see that the angle between the normal force and the displacement is 90? So this has to be the cosine of 90 degrees. That's 0. So the work done by the normal force, 0 joules. Okay? Go on to the next one. Gravity is 50 newtons. Straight downwards. Box slides 10 meters along the ramp. What is the angle between the ramp and the weight? 60, right? It's a 30, 60, 90 triangle. I'm not trying to trick you. It's 60 degrees. You guys are sharp. You can put that together. That means this has to be the cosine of 60 degrees. 250 joules. Now, yesterday we were pushing the box up the ramp. Do you remember? And to push the box up the ramp, we had to apply a force along the ramp. And try as I might, some of you just absolutely refuse to do what I ask sometimes. Meaning, if I asked you right now, what is the magnitude of the component of the force down the ramp, the portion of gravity this way, how many of you can just rattle it right off? It's either mg sine or mg cosine. Can you do it? Because if you can't, you're not doing what I've asked. I've told you just to memorize the two components. Mg sine theta is down the ramp. Mg cosine theta is into the ramp. If you have not internalized that, if you've not memorized that, what are you waiting on? You want me to put 20 more multiple choice questions on there so you have to do it from memory because you don't have time to figure it out? Memorize it, please. The reason I'm saying that to you is that when I talk about the fact that the thing down the ramp is mg sine theta, are you able to discern that that theta is not the theta that we've been using over here? There's a different theta. That theta is just a placeholder for area, for angles. This theta represents the angle of the ramp. This theta represents the angle between the displacement and the force doing the work. We use theta for every angle. Every one of them. So you've got to know what each thing is. Either way, can't we see that the force down the ramp is 50 times the sine of 30 degrees? That's the component of weight down the ramp, which is 25 newtons. If I look at just this component going down the ramp, getting back to this, look, the weight of the object down the ramp was 25 newtons, and the ramp is 10 meters long. If I just talk about the component of the force going down the ramp, do you see I also get 250 joules of energy? That doesn't really matter how you slice this thing up. You're going to get the same answers all the time. But also, to get up to the top there, do you realize you have to do 250 joules of work to get it to the top? That if I wanted to push the box this way, that I would have to push with 25 newtons of force to get it to go up the ramp. And that if I pushed with those 25 newtons of force, and I pushed it up the ramp 10 meters, that I would have to do 250 joules of work. Now, if that's not enough to see that what's going on here, then allow me to do one more thing. What if I wanted to just take the box and lift it straight up to here, how much work would be done doing it that way? You'd have to know some things, wouldn't you? You'd have to know, like, how high you're lifting the box. Can you figure that out for me? Because you know about triangles and can figure out the length of this side. I mean, hypotenuse is 10 meters, angle 30 degrees. Is it too much to realize that that's 5 meters? And how heavy is the box? 5 kilograms, right? So its weight is how many newtons? 50. So if I wanted to lift the box up, how many newtons of force would I have to apply to the box to lift it up? 50 newtons times 5 meters. How many joules of energy? 250. Yeah. Yeah. Getting the box to the top of the ramp takes the same amount of energy, whether I lift it straight up or I slide it up the ramp, as long as there's no friction. Now, there's friction, that would not be true. Because if there was friction, it probably wouldn't act if I'm just lifting it up, not sliding against the surface. But it would act if I'm trying to slide it up the ramp. The first takeaway that I need to put in your notes here, because this is a valuable piece of information, is that that's what simple machines do. The ramp is still a simple machine. And as I said to you guys earlier with simple machines exchange force for distance. But there was more to that statement. I just couldn't talk about it at that time because that was 3 weeks ago. Simple machines exchange force for distance while doing the same amount of work. While doing the same amount of work. So whether I lift the box straight up or I slide the box up the ramp, takes 250 joules of energy. The difference is I can push with a lot less force if I slide it up the ramp. It's half the amount of force than if I lift it straight up. It weighs 50 newtons. But if I slide it up the ramp, I only have to push with 25 newtons. But I have to push it twice as far to get it to the top of the ramp than if I can just lift it up to the top of the ramp. Simple machines exchange force for distance while doing the same amount of work. That's true whether it's a ramp, a lever, a pulley, or a wheel and axle. They all exchange force for distance while doing the same amount of work. Now, we're not going to spend much more time on that, but I do want you to recognize that if I do let the box slide down the ramp, you should be able to tell me how fast it's going at the bottom of the ramp. Right? Change in kinetic energy. So, yes?
Would that mean that they're inverses of each other? In the equation for force, distance equals work?
For a simple machine, sure. So, I'm not asking for you to do very much. If the box slides down the ramp, what is the change in the kinetic energy of the box? I said this like 20 times out loud. 250 joules. So, change in kinetic energy, 250 joules. You can figure out how fast it's going. Come on. Keep up with me. I don't really care what the number is, but does it matter whether I let it slide down the ramp or I push it off the edge? If I push it this way and it falls off the ramp, how much work is done bringing it to the ground? I can let the silence go on all day. Yeah, I can, but let me I do work on the box so that it has a change of kinetic energy that results in a velocity of 4 meters per second. It's going towards a ramp angled 30 degrees. And I choose 30 degrees to make it easy on you. You understand, right? If I'm the book, I could do 37.4 or some garbage like that, but I don't care about making the angle something interesting. Can you tell me how high up the ramp it goes before it stops? I want the number that goes with the question mark. I don't know if you can do this or not, but everything you need to do this is sitting right there in front of you. Talk with your friend. When you guys did that, you figured out that the box had 80 joules of energy. Is that what you did? I'm just not sure. Do it the same way you did, but the box has 80 joules right now. 1/2 mv squared, right? Am I wrong? Okay. Just figure I'd start someplace and see. All right, so 40 joules of energy. And the work done on the box has to equal negative 40 joules of energy in order to bring the box to rest. Is that what you assumed? So at what point did you guys start figuring out which force to use? Which force did you use? Like you set this equal to what? Because it's got to be force times distance times the cosine of the angle. Something did work on it. Did you do it this way? What'd you use for the force acting on it? How much? 50. So the weight of the box is 50 newtons, okay? We don't know D, so what'd you use for the cosine? 120, excellent. I don't know that everybody was gonna do that. I'm happy to see that some people did. It's not the only way to do it, but this would have worked. And if you don't know why these choices have been made, the box was going this way. That's the direction of the displacement. The weight is this way, so this has to be 120 degrees. Now, I'm sure not all of you did it this way. In fact, I am absolutely positive not all of you did it this way. But I'm happy to see some people did it this way because it works out just perfect. Now, if you didn't do it this way, you could have also said, all right, the force acting on the box is mg sine theta. You could have done it like this. That would have been 50 times the sine of 30 because this is the force from the component of force down the ramp from gravity. And then D, and then the cosine of 180 degrees. That would have been okay. Would have given you the exact same answer. You're still going to get that 1/2 in there and the negative sign. There's probably another way to do it too that people from last year might have done it. They might have figured out how high the box goes and then use that to figure out how far along the ramp. And that would work too. All right. So I think I can move on then. This one isn't terrible, right? Here's how the problem begins. It's a 5 kilogram cannonball fired upwards at 35 meters per second. And I believe what they're interested in is the velocity of the cannonball after it has traveled 45 meters in the air. But we're going to ask several questions about it. So the first question I'm going to ask is, what work is done on the cannonball? And then what is the change in kinetic energy of the cannonball? And what is the new speed of the cannonball? I don't know what the actual problem asks, but those would be the things I would expect. So I think this will answer your question. Is that going to work out okay? All right, so we'll start with the first question. What work is done on the cannonball as it rises 45 meters? So in considering that question, the work done requires us to consider the forces acting on the object over the displacement of the 45 meters. And in looking at this question, I can only think of one force that is consistently acting on the cannonball over this displacement of 45 meters, and that's got to be the weight of the cannonball. Now, don't get confused. There's two different arrows here. They are not the same thing. One of them is the velocity. The green one is the force. So as a free body diagram goes, this would be a fail at a free body diagram. The free body diagram on the cannonball would just be a single arrow downwards with its weight, mg. That'd be the free body diagram. So let's not get them confused. You're not supposed to put a velocity on a free body diagram. But aside from that, the work done is going to be the force of gravity. And I know I've been writing F with a G here. It's just for the time being. I don't want you to confuse that with a capital W that you might think means work. Does that make sense? So I'm just for right now. I will go back to putting just mg or w, but I'm trying to give us kind of a framework. There's three parts to work. There's the size of the force. There's the displacement, in this case, a delta y, which is what they use in the book. And I'm going to try and be consistent with the book for this example so I can kind of talk about what the book is saying. The book is saying that it changes its y displacement. So they're using y to indicate a vertical change in height. I would probably just put an h here for the height, but I'm going to be consistent with the book, and they use delta y. And then there's the cosine of the angle, and this is the angle between the displacement and the force of gravity. So when I go to fill in all these pieces, the force of gravity is going to be, I'm going to do 50, but it's probably 49 in the book, because they probably use 9.8, but 50 works for me, I hope. If you'd like, we can use 49. It's up to you guys. All right, so 50 newtons. The displacement is upwards, and it's 45 meters. But here's where I need to be a little bit cautious. The cannonball traveled upwards, so the displacement is upwards, but the weight was acting downwards the whole time. So the angle between the displacement, delta y, and the weight, well, that's 180 degrees. So I got to put the cosine of 180 degrees here. Now, this involves you guys doing like multiplying and stuff, but I'm thinking it's 2250. Is that right? I need you to verify it. But okay, 2250. Yep. But it is negative, and the unit will be joules. This is the work done by gravity on the cannonball. Yes.
Why is it negative?
Because of the cosine of 180. That makes it negative. And it's what this work is going to do on the cannonball that I think is important. This is the only force that acts on the cannonball after it's been launched. There was something that acted on the cannonball in order to launch it, but after it's been launched, this is the only force that acts on the cannonball. I know the cannonball is going to slow down. I expect its kinetic energy to get smaller. Eventually, it's going to stop when it gets high enough. So the work done has to be negative to reflect the fact that the cannonball is going to be losing kinetic energy as it goes upwards into the air. Because I'm expecting the velocity to become a smaller number. So the framework here is to indicate that changes in kinetic energy is what drives our definition of work. When you do positive work on something, you're trying to increase how fast it's going. If you do negative work on something, you're trying to decrease how fast it's going. Gravity certainly is trying to decrease how fast the cannonball is going while it goes upwards. Now, there's more to do here, but The change in kinetic energy is also negative 2,250 joules. And the reason this is true is not necessarily what you think. The reason this is true is because there's only one force acting on the cannonball. If there were other forces acting on the cannonball, we would have to calculate their work on the cannonball separate and then add them together. Or we would have to already know the final velocity of the cannonball. I'm being very careful here. This question, the change in kinetic energy, there's two different ways to get to the answer. One of them is to know the work done by all other forces acting on the object. That gets us the net work. Or we have to already know the final velocity of the cannonball. It's the only way we're going to know what the change in kinetic energy is. But we know this is the only force acting on the cannonball, so now we could use that to figure out the new speed of the cannonball. So to figure out the new speed of the cannonball, I'm going to need the old speed. I just moved it out of the way, 35, right? So I'm going to set this equal to 1/2 mv final squared minus 1/2 mv initial squared. And I know I don't normally use the f and the I. I usually use just nothing or a naught. I want to be very explicit. It's final minus initial here. That's important. And that's to keep us consistent. And we have 1/2 times 5 times v final squared minus 1/2 times 5 times 35 squared. And that equals negative 2250. So now we just have to figure out what that final velocity is. Is that enough? Is that thorough enough? Obviously, what's that?
The book did it like a different way.
What they're showing you in the books. So I'm just going to move this over to here, and that should be sufficient. Somebody, if you just work this out, can somebody tell me what this is? It's like 3,000 something, right? 3,062? 3,062.5. So this is negative 2250 equals 1/2 mv final squared minus 3,062.5. Okay? So what you had to do, of course, was get this to the other side. So we'd have 1/2 mv final squared equals negative 2250 plus 3,062.5. I'm just writing that stuff on the other side because I'm out of space. Is everything okay so far? This represents the final kinetic energy. This represents the work done by gravity. And this represents the initial kinetic energy. Those are the three things that were involved in this problem. Now, I'm not sure they did it any different. They, instead of just looking at it from the difference, they solved it more symbolically this way first. Subtracting KE from both sides still gives you K final minus K initial, which is still our definition of total work. It's still the same. They just aligned it a little bit differently in their algebra, but it's still the same kind of thing. Is that all right? Everybody good on that?